What if I told you there are places in the universe so mysterious, so unreachable, that even our most advanced technology can barely scratch the surface of their secrets? Imagine vast regions hidden by cosmic fog, endless stretches of emptiness, or phenomena so powerful that they defy the very laws of nature as we understand them. These are not just distant dots on a telescope's map. They are cosmic enigmas that challenge everything we think we know about the universe. In this video, we're taking you on a mind-bending journey through 15 regions of the cosmos that remain utterly unexplored, not because of a lack of curiosity, but because the universe itself has drawn impenetrable boundaries around them. From immense voids and radiant quasars to the edge of the observable universe and even speculations about the multiverse, these regions lie tantalizingly out of reach. Yet their inaccessibility only fuels our fascination. What makes these places so impossible to explore, and what secrets might they hold? Stay with us as we unravel these mysteries, diving deep into the cosmos to uncover the unreachable. Each region we explore will leave you questioning not only the universe but also the limits of human discovery. Let's embark on a journey to the unknown. Now turning to the Boötes Void, this mysterious cosmic region is unlike anything else in the observable universe. Located in the Boötes constellation, this vast expanse of near emptiness stretches across hundreds of millions of light years, earning it the nickname Cosmic Desert. To put its scale into perspective, if our Milky Way galaxy were placed inside this void, it would stand virtually alone, surrounded by unfathomable emptiness. What makes the Boötes Void so perplexing is the sheer lack of galaxies within its bounds. While the universe is generally structured with galaxies clustering together, connected by cosmic filaments, this region defies that norm, presenting an eerie and almost incomprehensible nothingness. Scientists have theorized about its formation, with some suggesting it could have resulted from large-scale cosmic mergers that swept galaxies away, leaving behind this void. Others speculate that it might simply be a natural anomaly, a rare but randomly occurring pocket of emptiness. Despite these theories, its true nature remains unresolved. The immense distance and scarcity of matter within the Boötes Void make it impossible to explore directly with our current telescopes or space probes. It exists as an elusive question mark in the cosmic map, a silent reminder of how much we have yet to understand about the universe's structure and evolution. As the next challenge unfolds, the Boötes Void presents a daunting puzzle for scientists attempting to study it. Its staggering distance, combined with its lack of observable matter, poses significant limitations for even the most advanced telescopes. Traditional optical telescopes struggle to detect much in this region due to the absence of bright galaxies or stars to observe. Even radio telescopes, which excel at peering into the depths of the cosmos, find little to detect in this vast expanse of silence. Without nearby objects to reflect or emit detectable signals, the void remains largely invisible, like trying to map an empty, pitch-black ocean with just a flashlight. Space probes, which have provided invaluable data about closer regions of space, are not even close to reaching distances of this magnitude. The Boötes Void lies hundreds of millions of light years away, far beyond the reach of any instrument we can currently deploy. Given these hurdles, scientists rely heavily on indirect methods to study this enigmatic region. They use complex computer simulations to model galaxy formation and distribution, tweaking variables to see if they can recreate similar voids in their digital universes. These models suggest that such vast emptiness could result from the merging and movement of galaxy clusters over billions of years, creating a cosmic ripple effect that left this void behind. However, these are just educated guesses shaped by the limits of our technology and understanding. Another approach involves studying the gravitational effects the void has on its surroundings. While invisible to us, the void's low-density region can slightly influence the motion of nearby galaxies, offering subtle clues about its size and structure. Each piece of data collected brings us a step closer to deciphering its secrets. Yet, for now, the Boötes Void stands as a stark reminder of the limitations of human technology and the vastness of the unexplored universe, teasing us with questions that may remain unanswered for generations to come. Moving forward, we encounter another enigma hidden closer to home, shrouded behind the dense veil of our own Milky Way galaxy. Now turning to the Zone of Avoidance, we delve into a region of the universe that remains frustratingly veiled from our gaze. Nestled within the sprawling plain of our own Milky Way galaxy, this mysterious area is cloaked by an impenetrable curtain of gas and dust. This dense cosmic fog acts as a formidable barrier, blocking visible light from passing through and rendering traditional optical telescopes almost useless in observing what lies beyond. The name itself, the Zone of Avoidance, arises from this very challenge. Astronomers quite literally avoid mapping this area because their instruments can glean so little from it. But why does this matter? Scientists theorize that hidden behind this cosmic obscuration could be a treasure trove of undiscovered galaxies, clusters, and perhaps other cosmic phenomena that might reshape our understanding of the universe's structure and history. The Zone of Avoidance has long piqued astronomers' curiosity because its location aligns with the large-scale distribution of galaxies, suggesting it may conceal significant cosmological activity. Unfortunately, even the most advanced telescopes packing infrared and radio detection technology, which are typically better at piercing through dust, face limitations in fully unveiling this concealed realm. What makes this especially intriguing is the possibility that some of these hidden galaxies might belong to massive structures influencing the gravitational forces on a scale we have yet to fully comprehend. In essence, the Zone of Avoidance could hold answers to some of the most fundamental questions about the universe. Yet, like a locked chamber whose key eludes us, this region remains a maddening puzzle, inviting speculation but defying exploration. As we continue unraveling the mysteries of the cosmos, we must turn to innovative tools and techniques to peer beyond this dense veil. Moving forward, we explore how astronomers are pushing the limits of technology in their relentless pursuit to uncover the secrets buried in this enigmatic expanse. With the next phase of the journey in sight, we turn to the innovative efforts astronomers have made to peer through the Zone of Avoidance's thick veil. By employing infrared and radio telescopes, scientists have tried to circumvent the limitations of traditional optical instruments, which fail against the dense curtain of gas and dust. Infrared telescopes, capable of detecting heat instead of visible light, have offered glimpses into this hidden region by unveiling the faint glow of objects concealed by the cosmic fog. Similarly, radio telescopes, adept at capturing longer wavelengths, have been instrumental in mapping celestial structures obscured to the naked eye. These tools have provided valuable insights, identifying partial outlines of galaxies and piecing together fragments of the larger puzzle. However, as groundbreaking as these technologies are, they still face significant hurdles. The density of cosmic material in certain areas remains too overwhelming, even for these advanced instruments, leaving substantial gaps in our understanding. Moreover, because these methods rely on indirect observation, the data they provide often require careful interpretation, leading to uncertainties and theories that are challenging to confirm. Despite these obstacles, the successes achieved so far are nothing short of remarkable. Scientists have uncovered evidence of hidden galaxies and faint cosmic structures that suggest the Zone of Avoidance holds far more than just empty space. It could be home to a bustling region of cosmic activity. Yet, for all we have revealed, the region remains largely enigmatic, a testament to both the progress we have made and the limits of our technology. This ongoing struggle to penetrate the Zone of Avoidance is a vivid reminder of how much there is still to discover and the ingenuity required to push the boundaries of our cosmic exploration. As we look to the horizon, our journey presses onward to explore even more baffling and inaccessible corners of the universe. Moving forward, we arrive at the heart of our own galaxy, a region dominated by one of the most profound cosmic marvels, Sagittarius A*, the supermassive black hole anchoring the center of the Milky Way. This colossal entity, millions of times more massive than our Sun, exerts a gravitational pull so intense that it governs the motion of stars, gas, and dust in its vicinity, shaping the very structure of our galaxy. Yet, this immense gravitational force is precisely what makes any attempt at close exploration utterly impossible. Any spacecraft venturing too near would encounter the event horizon, a boundary where the pull of gravity becomes inescapable, even for light itself. Crossing this point would result in spaghettification, a term used to describe the extreme stretching of matter in the presence of such overwhelming gravity, leaving no hope of retrieval or survival. Beyond its physical dangers, Sagittarius A* is an environment teeming with high-energy radiation and chaotic magnetic fields, further solidifying its status as an unreachable frontier in space exploration. This mysterious powerhouse not only serves as the dynamic core of the Milky Way, but also offers scientists a living laboratory to study phenomena like relativistic jets and the warping of space-time itself. Despite its inaccessibility, indirect observations using advanced telescopes have unlocked valuable insights into its behavior, helping us understand how supermassive black holes influence their host galaxies. However, these glimpses only scratch the surface of its secrets. Sagittarius A* remains an enigmatic force, a powerful reminder of the universe's most extreme realities and the formidable challenges they pose to our quest for understanding. As the next challenge unfolds, let us delve deeper into the theoretical obstacles that make Sagittarius A* a realm forever beyond our grasp. At the center of this cosmic enigma lies the event horizon, a boundary that represents the point of no return. Once crossed, the immense gravitational pull ensures that nothing, not even light, can escape. The physics of this region push our understanding to its limits, as conventional laws of nature give way to the extreme warping of space and time. One of the most haunting phenomena theorized to occur near the event horizon is spaghettification. This is the process by which any object, whether a spacecraft or even an atom, would be stretched into a thin, elongated strand due to the overwhelming difference in gravitational forces acting on different parts of it. Imagine being pulled apart molecule by molecule with no hope of resistance or recovery. But even before reaching such a fate, the intense radiation and turbulent magnetic fields surrounding Sagittarius A* would obliterate any spacecraft attempting an approach. These factors make the black hole not just physically unreachable, but also a lethal environment for even the most advanced technology. Yet, despite these insurmountable barriers, Sagittarius A* continues to captivate scientists as a theoretical playground. Its behavior offers invaluable clues about the nature of gravity, space-time, and the evolution of galaxies. By observing its effects on nearby stars and gas clouds, researchers can indirectly study phenomena like relativistic jets and gravitational lensing. These insights challenge us to rethink fundamental principles and test the predictions of Einstein's theory of relativity in ways no Earth-bound experiment ever could. However, this makes it all the more tantalizing and frustrating that we will never truly experience this cosmic colossus firsthand. In many ways, Sagittarius A* serves as a powerful reminder of the limits of human ambition when faced with the most extreme forces in the universe. It is both a source of inspiration and a humbling testament to the vast, untamed nature of the cosmos. With these challenges in mind, we now look outward to another frontier, where mysteries are obscured not by gravity but by the dense veil of our own galaxy. Moving forward, we venture to the theoretical edges of our solar system, the Oort Cloud. This vast, hypothetical cloud of icy bodies is believed to encase our solar system like a frosty, celestial shell. It is considered the outermost boundary of the Sun's gravitational influence, marking a region where the pull of our star begins to wane and interstellar space takes over. Scientists propose that the Oort Cloud could extend tens of thousands of times farther than the distance between the Earth and the Sun, placing it in a realm of almost unfathomable remoteness. Within this distant frontier lie countless icy objects, thought to be the ancient remnants from the solar system's formation billions of years ago. These silent wanderers, possibly numbering in the trillions, may serve as cosmic archives of our origins. Yet the Oort Cloud remains entirely speculative. No spacecraft has ever ventured far enough to confirm its existence, nor have telescopes been able to directly observe it due to its immense distance and the faintness of the objects within. All we have are indirect clues, like the trajectories of long-period comets that sweep into the inner solar system, which seem to trace their origins to this mysterious outer boundary. The sheer distance and lack of observable evidence make the Oort Cloud one of the most elusive regions of our cosmic neighborhood. It challenges us to stretch the limits of our imagination and technology to one day confirm its existence and unravel the secrets it might hold about the very beginnings of our solar system. With the next phase of the journey in sight, the Oort Cloud stands as more than just a boundary. It is a potential key to unlocking the mysteries of our solar system's earliest days. Scientists believe that many of the long-period comets, those icy travelers that occasionally grace our skies, originate from this distant realm. These comets are like messengers, carrying with them pristine materials that have remained largely untouched since the solar system's birth. By studying them, we gain valuable insights into the composition and conditions present at the dawn of our cosmic neighborhood. Yet, directly exploring the Oort Cloud remains a monumental challenge. Its extreme distance, combined with the immense size and faintness of its inhabitants, makes it nearly impossible to reach with current technology. Even our most advanced spacecraft, traveling at their highest speeds, would require thousands of years to traverse the vast expanse separating us from this hypothetical shell. Beyond the sheer distance, the overwhelming sparsity of objects within the Oort Cloud makes finding and studying individual targets an almost insurmountable task. These icy bodies drift through an ocean of emptiness, their faint presence easily lost against the backdrop of interstellar space. The technological leaps required to send probes capable of surviving such a prolonged and distant mission are staggering, demanding advancements not just in propulsion and power systems, but also in autonomous navigation and communication over unparalleled distances. However, as science continues to push the boundaries of possibility, one day we may bridge the gap to this elusive frontier. The Oort Cloud, while invisible to us now, holds the promise of illuminating the ancient history of our solar system, a story waiting to be revealed if only we can find the means to reach it. Moving forward, we encounter the enigmatic realm of dark matter halos, vast, invisible structures that are believed to envelop galaxies like unseen cocoons. Unlike the stars and planets we can observe through telescopes, dark matter does not emit, absorb, or reflect any light, rendering it undetectable by conventional means. Its presence is inferred solely through its gravitational effects, which influence the motion of stars and galaxies. Imagine a spinning galaxy. Without the additional mass provided by dark matter, the outer stars would scatter away, unable to maintain their orbits. Yet they remain bound, as though an invisible scaffold is holding the galaxy together. This is the evidence pointing to the existence of dark matter halos. Scientists have observed countless galaxies behaving in ways that only make sense if surrounded by this mysterious substance. Despite their suspected presence all around us, dark matter halos remain beyond our reach. Current technology provides no way to observe or directly measure this invisible mass. The challenge lies in its very nature. We are dealing with something that interacts with regular matter only through gravity, making it elusive even to the most sensitive instruments. While telescopes and detectors help trace its indirect effects, the prospect of directly exploring or even interacting with dark matter halos is far beyond our present capabilities. Direct exploration would require technologies that still reside in the realm of speculation, potentially harnessing methods we cannot yet imagine. These halos are not just cosmic curiosities. They are integral to the formation and evolution of galaxies, shaping the universe on the largest scales. Understanding them could unlock profound answers about the fundamental makeup of the cosmos itself. Yet, for now, they remain the universe's silent and unseen architects, a riddle wrapped in gravity that continues to evade our probing curiosity. As we delve deeper into the unknown, the search for understanding what lies behind this invisible force drives us to the cutting edge of scientific discovery, pushing the boundaries of what we think is possible. With the next phase of the journey in sight, we turn our attention to the ingenious methods scientists employ in their quest to uncover the secrets of dark matter. Since this elusive substance refuses to interact with light or any form of electromagnetic radiation, researchers have devised indirect approaches to study its effects. One such technique involves observing the rotation of galaxies. Scientists have discovered that the outer regions of galaxies rotate at speeds far greater than what visible matter alone can account for. This discrepancy hints at the gravitational pull of an unseen mass dark matter that holds these galaxies together. Another powerful tool is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from distant galaxies travels through the universe, it bends around massive objects like a lens, creating distortions in the light we observe. By analyzing these distortions, researchers can map the distribution of dark matter, even though it remains invisible to our eyes. Despite these advances, the quest to study dark matter is fraught with limitations. Both galaxy rotation curves and gravitational lensing provide indirect evidence, meaning we are interpreting its presence based solely on its effects on other objects. This leaves us with only a partial picture of its true nature. Moreover, dark matter detectors on Earth, designed to capture fleeting interactions between dark matter particles and regular matter, have yet to yield conclusive results. The challenge lies in the fact that dark matter interacts so weakly with everything around it, except through gravity, that detecting it is like trying to catch a whisper in the middle of a storm. This profound mystery continues to fuel the imagination of scientists and challenges the boundaries of what we can achieve. Understanding dark matter could redefine our comprehension of the universe, potentially revealing a hidden framework that has shaped cosmic evolution from the very beginning. Yet, for now, the search for dark matter remains an intricate puzzle, one that underscores the vastness of what we do not yet know. With each discovery, however small, we edge closer to unveiling one of the universe's most enduring enigmas. As we leave this unseen realm behind, our journey into the cosmos moves forward toward yet another region of wonder and mystery. Now turning to the next chapter of our cosmic exploration, we encounter the cosmic microwave background, often referred to as the afterglow of the Big Bang. This faint radiation, a relic from nearly 14 billion years ago, permeates the universe and provides a snapshot of the cosmos when it was merely 380,000 years old. Often described as a time capsule, the cosmic microwave background holds vital clues about the early universe, its composition, structure, and even the processes that shaped everything we observe today. By studying this ancient light, scientists have been able to pinpoint the universe's age, confirm its expansion, and uncover evidence of dark energy. Yet, despite its significance, the cosmic microwave background remains an untouchable frontier. Unlike regions of space that we might one day physically visit, this radiation exists as an ethereal echo, an imprint of an era so distant that it cannot be directly explored. The light we observe from the cosmic microwave background has stretched and cooled over billions of years, becoming faint microwaves that can only be detected with incredibly sensitive instruments. This means that the cosmic microwave background is not a place we can ever travel to, but rather a veil of ancient information. It exists as the final curtain, beyond which no light or matter could pass unscattered before the universe became transparent. And while it keeps its secrets from direct exploration, its faint whispers of light allow us to probe the cosmos' infancy in ways that continue to push the limits of human ingenuity. As we move beyond this ancient afterglow, the story of the universe beckons us further toward phenomena just as profound and enigmatic. Moving forward, let us look at how scientists have managed to map and study the faint whispers of the cosmic microwave background, unlocking insights from nearly 14 billion years ago without ever setting foot in this unreachable frontier. Specialized satellites such as the Planck telescope have been pivotal in this mission. These instruments are designed to detect the faint microwave radiation that blankets the universe, capturing data with astonishing precision. By analyzing temperature fluctuations and variations in the cosmic microwave background, researchers create detailed maps of the early universe, like a cosmic blueprint that reveals how matter began to clump together, forming the seeds of galaxies and stars we see today. However, this task is anything but straightforward. The signal from the cosmic microwave background is incredibly faint, competing with cosmic noise from stars, galaxies, and even our own atmosphere, making it a monumental challenge to isolate and study. To overcome this, satellites like Planck must operate in space far from Earth's interference, and they require cutting-edge technology to filter out distractions, allowing the ancient light to speak for itself. But interpreting the data presents yet another challenge. The patterns in the cosmic microwave background are like a puzzle with countless pieces. Each fluctuation holds information about the universe's density, composition, and temperature during its infancy. Scientists use complex mathematical models and simulations to decode these signals, piecing together a story of how the cosmos evolved from its earliest moments. Still, despite these advances, the cosmic microwave background remains just out of reach for any direct interaction. It is a window into the past that we can observe but never touch, a reminder of the limits of exploration and the boundless possibilities of discovery through observation. With this glimpse into the early universe laid out before us, we now venture toward the next chapter of cosmic intrigue, where gravitational forces shape phenomena that pull not just in space, but across the mysteries of time itself. Now turning to one of the most perplexing phenomena in the cosmos, we encounter the Great Attractor, a hidden gravitational anomaly that exerts a powerful pull on galaxies in our local universe, including our own Milky Way. Located roughly 150 million light-years away in the direction of the Centaurus constellation, this enigmatic region is a key player in the large-scale motion of galaxies. Imagine vast galactic clusters like the Milky Way and its neighbors, all hurtling through space at incredible speeds, seemingly drawn by an invisible hand. The Great Attractor's immense gravitational influence creates a flow of galaxies, often referred to as the cosmic migration, yet its exact nature remains cloaked in mystery. What we do know is that this region contains an extraordinary concentration of mass, likely making it home to a dense cluster of galaxies or even something far stranger. However, the vast distance and its shrouded location, partially obscured by the gas and dust of the Milky Way's zone of avoidance, make direct exploration impossible. Even the most advanced telescopes struggle to peer through the dense cosmic fog that veils this region. Instead, scientists rely on indirect methods like mapping the movements of galaxies around it to deduce its gravitational footprint. This anomaly raises profound questions about the unseen structures that shape the universe's architecture. What could lie at the heart of the Great Attractor? Perhaps it holds clues about the distribution of dark matter, the mysterious invisible substance that dominates the universe's mass. Or maybe it is simply a massive galactic supercluster, one of many scattered across the cosmic web. Although we may never get close enough to solve its riddles, the Great Attractor reminds us of the hidden forces that shape our universe, pulling galaxies across the fabric of space-time. As we marvel at this gravitational enigma, our journey continues toward the unyielding brilliance of quasars, where light from the distant past illuminates one of the universe's most extreme phenomena. As the next challenge unfolds, we delve deeper into the complexities of the Great Attractor, a mystery that only grows with its partial concealment behind the Zone of Avoidance. This dense region of gas and dust within our Milky Way acts like a cosmic curtain, blocking visible light and leaving much of what lies beyond shrouded in darkness. Traditional optical telescopes struggle to penetrate this obscured zone, making it extraordinarily difficult to study the Great Attractor directly. However, scientists have turned to innovative tools like X-ray and radio telescopes to peer through this veil. These specialized instruments can detect wavelengths of light invisible to the human eye, allowing researchers to uncover faint signals that hint at the colossal structures hidden in the depths of space. By analyzing X-ray data, astronomers can identify clusters of galaxies and determine their mass, revealing the gravitational forces at play. Meanwhile, radio telescopes help trace the motion of gas and celestial objects, giving scientists a clearer picture of the region's dynamic interactions. Even with these advances, the Great Attractor remains an enigma, as the information gathered is often fragmented and incomplete. It is like assembling a puzzle with most of the pieces missing, challenging researchers to make sense of a cosmic phenomenon that defies clear observation. Despite the obstacles, these efforts underscore humanity's relentless curiosity and determination to understand the forces shaping our universe. What could possibly thrive in a region so obscured and unreachable? Could it hold insights into the long-sought nature of dark matter, or perhaps new clues about the evolution of the cosmos? While these questions linger unanswered, they propel us forward, driving scientific innovation and keeping the quest for knowledge alive. Moving forward, we step into the realm of quasars, where unimaginable energy and the light of ancient times unveil another extreme corner of the universe's mysteries. With the next phase of the journey in sight, we turn to quasars, the universe's dazzling powerhouses that illuminate the cosmos with their almost unimaginable energy. Quasars are among the brightest and most distant objects ever observed, their brilliance powered by supermassive black holes at the centers of galaxies billions of light-years away. These black holes, surrounded by swirling disks of gas and dust, generate immense energy as matter falls toward them, heating up to extreme temperatures and releasing intense radiation. This radiation is so powerful it outshines entire galaxies, making quasars visible across vast cosmic distances. However, their very nature makes them impossible to approach or explore. The extreme radiation emitted by quasars creates an environment so hostile that no known spacecraft or technology could survive the journey. Moreover, the staggering distances that separate us from these celestial giants, measured in billions of light-years, place them firmly beyond our reach. Even traveling at the speed of light, it would take billions of years to arrive at the location of a quasar, assuming such a feat were even theoretically possible. Despite these limitations, quasars offer a unique window into the early universe. Because their light has traveled across such immense distances to reach us, observing quasars is like peering back in time, giving scientists valuable insights into how galaxies formed and evolved. Yet, for all the knowledge they provide, quasars remain as much a mystery as they are a marvel. What other secrets might these radiant beacons hold about the history and structure of the cosmos? The answers may forever elude us, but the questions they inspire continue to drive our exploration of the unknown. Now, as our journey unfolds further, we venture to the Andromeda core, a turbulent realm that offers its own set of cosmic challenges and revelations. Peering into the past through the light of quasars is like unlocking a time capsule of the universe, revealing what it looked like billions of years ago. Since the light from these distant objects has taken such an extraordinary amount of time to reach us, we are essentially observing them as they were in the distant past. This phenomenon offers scientists an unprecedented glimpse into the early stages of galaxy formation, black hole activity, and even the composition of the universe when it was still in its infancy. By studying quasars, researchers can piece together clues about how galaxies evolved, how supermassive black holes shaped their surroundings, and how the universe transitioned from its chaotic beginnings to the vast structures we see today. However, the observational method comes with significant limitations. The incredible distances and immense spans of time involved mean that the information we gather is not only ancient but also incomplete. The light we see from quasars tells us nothing about their present state or what might have occurred in the eons since their light began its journey toward us. Additionally, the extreme brightness of quasars can obscure details about the galaxies that host them, leaving some of their surrounding mysteries unsolved. And while telescopes can capture their brilliance, no spacecraft could ever hope to reach these regions for direct exploration, as the distances are utterly insurmountable. These challenges ensure that quasars will forever remain as untouchable as they are illuminating, offering only fleeting snapshots of a distant and inaccessible past. Still, the allure of these cosmic time machines lies in their ability to inspire new questions about the origins and evolution of the universe. With the next phase of the journey in sight, we now turn to the Andromeda core, where the heart of our galactic neighbor holds its own set of mysteries waiting to be unraveled. With the next phase of the journey in sight, we now turn to the Andromeda core, the turbulent heart of our closest galactic neighbor. At the center of the Andromeda galaxy lies a formidable supermassive black hole, a cosmic giant with a gravitational pull so intense that it dominates the surrounding region. This galactic core is a realm of extreme forces where matter spirals at immense speeds, heating up to millions of degrees and releasing powerful bursts of radiation. The environment here is nothing short of hostile, with conditions so severe that no spacecraft could hope to survive the journey, let alone send back data. Even the most advanced shielding would falter against the relentless onslaught of high-energy particles and deadly radiation. The immense gravitational forces around the black hole create violent tidal disruptions, ripping apart anything that drifts too close. This chaotic region also serves as a crucible for stellar activity, with stars forming, colliding, and being consumed in a dramatic cosmic ballet. Despite its dangers, the Andromeda core holds profound scientific significance. By observing it from a safe distance, astronomers can gain insights into how supermassive black holes influence their host galaxies, the dynamics of galaxy cores, and the interplay of forces in such extreme environments. Yet, direct exploration of this region remains beyond our reach, a vivid reminder of the limits of human ingenuity when faced with the sheer power of the cosmos. The mysteries of the Andromeda core echo the vastness of the universe itself, urging us to keep seeking answers while humbly acknowledging the boundaries of our exploration. Moving forward, let us explore the implications of Andromeda's future as it moves inexorably closer to our own Milky Way, setting the stage for an unprecedented cosmic event. As the next challenge unfolds, we dive into the future collision between the Milky Way and Andromeda, a cataclysmic event in the making that will forever reshape the structure of both galaxies. These two celestial giants are locked in a slow-motion dance, hurtling toward each other at speeds of hundreds of thousands of miles per hour. While this may sound like the prelude to chaos, the truth is both fascinating and complex. When Andromeda and the Milky Way eventually collide, roughly 4 billion years from now, it will not be a collision in the traditional sense. The vast distances between stars mean that few, if any, will actually make contact. Instead, the gravitational forces between these galaxies will interact, pulling and stretching their structure into a chaotic web. Entire star systems may be flung into new orbits, while others could be ejected into intergalactic space. At the core of this collision lies the fate of Andromeda's supermassive black hole and our own galaxy Sagittarius A*. The immense gravitational pulls of these two galactic centers will likely draw them together, merging to form a single, even larger black hole. This fusion of cosmic titans will release enormous energy, reshaping the surrounding regions. For the Andromeda core, this marks an explosive end to its current turbulent state as it merges into a newly formed galactic nucleus. While this process plays out on a cosmic timescale, the aftermath will result in a new galaxy altogether, a massive elliptical galaxy that astronomers have already dubbed Milky Way. Despite the dramatic nature of this event, life on Earth, if it still exists by then, may not even notice the changes. The sheer scale and duration of galactic collisions mean that these transformations occur over millions of years, far beyond a single human lifetime. This cosmic event underscores the dynamic nature of the universe, where even the majestic Andromeda core is not immune to change and transformation. But as awe-inspiring as this future collision may be, it remains an event beyond our ability to influence or explore directly, reminding us once again of the vast, unstoppable forces that shape the cosmos. Moving forward, our journey takes us to an even more remote and mysterious domain, where the emptiness between galaxies holds secrets of its own. Now turning to the vast, lonely void stretching between galaxy clusters, we encounter one of the most desolate regions of the universe, the empty spaces between galaxies. These immense chasms are not just empty in the ordinary sense, but are so sparsely populated that they seem almost devoid of matter altogether. Unlike the bustling neighborhoods of galaxies filled with stars, planets, and interstellar activity, these spaces are a near-perfect vacuum stretching across millions of light years. What makes these regions so enigmatic is their overwhelming lack of observable phenomena. There are no bright stars, no glowing nebulae, and no visible markers to anchor our understanding. They are so empty that direct exploration becomes virtually impossible. Even the most advanced telescopes capture only faint traces of light or radiation, making it a challenge to study these barren expanses. The reason behind their inaccessibility lies in their sheer scale. The distances involved are so staggering that attempting to traverse them with any current or foreseeable technology is far beyond our capabilities. These voids are not just gaps between galaxies. They are vast oceans of nothingness where even the speed of light takes millions of years to cross. Despite their emptiness, scientists believe these areas may still hold subtle clues about the nature of the universe. For instance, the faint glow of background radiation and the slight gravitational effects at the edges of these voids hint at the presence of dark matter or other hidden forces shaping the cosmos. Yet, much like the cosmic voids we've already explored, their secrets remain frustratingly out of reach. These intergalactic voids remind us of the universe's staggering scale and its ability to humble even our most ambitious efforts to understand it. But just as these empty spaces stretch toward infinity, our curiosity propels us forward to consider what lies beyond the boundaries of the observable universe, a frontier that challenges not just our technology but the very limits of what we can know. Moving forward, let us delve deeper into these intergalactic voids, often described as cosmic wastelands. While their emptiness might seem devoid of intrigue, scientists believe these vast expanses could hold untapped insights into the very fabric of the universe. One theory suggests that these voids may be crisscrossed by tenuous filaments of dark matter, an invisible substance thought to bind galaxies together. Though dark matter itself remains elusive, researchers analyze the gravitational effects seen at the edges of these voids to infer its presence. By studying how light from distant galaxies bends, what scientists call gravitational lensing, they can map out possible distributions of dark matter within and around these barren spaces. Beyond dark matter, these voids also act as a backdrop for studying the faint glow of cosmic microwave background radiation, the remnant heat from the Big Bang. Subtle fluctuations in this radiation as it passes through such empty regions offer critical clues about the early conditions of the universe. Additionally, some speculate that these voids may serve as natural laboratories for testing alternative theories of gravity or exploring phenomena that challenge our current understanding of physics. Despite the absence of visible activity, these spaces may house faint traces of particles, energy fields, or even undiscovered phenomena yet to be imagined. Yet, the profound distances and extreme emptiness make these theories difficult to confirm. For now, intergalactic voids remain enigmas, teasing us with their potential to unveil cosmic secrets while remaining physically and observationally out of reach. Our journey through these voids not only underscores the challenges of exploring the vast universe, but also sets the stage for an even greater frontier, the very edge of the observable cosmos, where the boundaries of what we can see and study are defined not by technology, but by the speed of light itself. With the next phase of the journey in sight, let us venture to the edge of the observable universe, a boundary defined not by physical barriers but by the very laws of nature itself. This cosmic horizon represents the farthest distance light has traveled to reach us since the beginning of time. Due to the universe's expansion, regions beyond this limit are moving away from us faster than the speed of light, rendering them eternally out of view. This means that no matter how advanced our technology becomes, we will never be able to see or explore what lies beyond this horizon. It is as though we are confined to a cosmic bubble, with the observable universe acting as the limit of our cosmic window. Within this boundary lies the light emitted from the earliest stars and galaxies, as well as the faint echoes of the Big Bang itself. Beyond it, however, lies an infinity that remains permanently hidden, its secrets locked away by the vastness of space and time. This limitation not only challenges our understanding of the cosmos, but also raises profound questions about the true scale of the universe. Are there countless galaxies, stars, and even civilizations thriving in these unreachable territories, or do these distant realms differ from anything we can imagine? While we may never obtain direct answers, studying the edge of the observable universe sharpens our comprehension of cosmic expansion and the forces shaping reality. It is a humbling reminder of our place in the grand scheme of existence, inspiring both awe and curiosity as we ponder the infinite possibilities that lie just beyond our reach. Moving forward, let us explore how this constant expansion of the universe challenges our ability to keep up with the ever-shifting frontier of what we can observe and understand. With the next phase of the journey in sight, let's delve deeper into the ever-expanding nature of our universe and its profound implications. As the universe continues to accelerate its expansion, more and more regions are pushed beyond our observable limit, vanishing from view forever. This relentless growth means that the light from many distant galaxies will eventually no longer reach us, no matter how powerful our telescopes may become. Over time, the observable universe will shrink in terms of the cosmic structures we can see, isolating us from an ever-increasing portion of the cosmos. This phenomenon is not only a result of distance, but also the fabric of space itself stretching faster than the speed of light. Imagine trying to catch up with a horizon that keeps moving as you race toward it. It's a pursuit that we are destined to lose. The accelerating expansion is driven by a mysterious force we call dark energy, a substance so enigmatic that it challenges our fundamental understanding of physics and reality. This force not only dictates how the universe evolves, but also determines the ultimate fate of everything within it. As vast portions of the cosmos slip beyond our reach, we are left grappling with questions about the nature of existence. What might these hidden regions contribute to the story of the universe? Could they shape its structure in ways we cannot observe or influence phenomena near our own cosmic neighborhood? This constant expansion underscores our limitations and serves as one of the greatest puzzles in modern astrophysics. Yet, despite this, the challenge inspires scientists to continue refining their theories, pushing the boundaries of knowledge, and searching for creative ways to peer into these unreachable realms. It reminds us that the act of exploring is as much about understanding what we cannot see as it is about observing what we can. Speaking of the furthest reaches of understanding, our attention now turns to a force in the universe that showcases both its beauty and its unpredictability: regions where gamma-ray bursts occur, unleashing unimaginable energy in an instant. Now turning to the next enigma, we arrive at the incredible phenomenon of gamma-ray burst zones. These regions are home to some of the universe's most powerful and mysterious events. A gamma-ray burst is a colossal explosion that can release, in just a few seconds, more energy than our Sun will emit over its entire lifetime. Such events are often triggered by the collapse of massive stars or the collision of neutron stars, remnants of ancient cosmic giants. The intense radiation emitted during a gamma-ray burst travels vast distances, often reaching us from billions of light years away, allowing astronomers to study these events as glimpses into the distant past of the universe. However, their true nature remains shrouded in mystery due to their fleeting and unpredictable nature. These bursts are so powerful that they can sterilize entire regions of space, rendering them utterly uninhabitable. Should such an event occur nearby, the intense radiation could strip away the atmospheres of planets and disrupt life as we know it. Fortunately, gamma-ray bursts are most commonly observed in distant galaxies far outside our cosmic neighborhood. But this distance also creates a barrier to direct exploration. The extreme danger posed by the radiation and the vast spans of time and space separating us from these zones make it impossible for any spacecraft to approach, let alone study them up close. Instead, scientists rely on sophisticated instruments like gamma-ray telescopes to detect these fleeting signals and piece together their origins and impact from afar. The very nature of these bursts, transient, destructive, and immensely powerful, highlights both the beauty and the violence of our universe. As we marvel at what little we can observe, we are reminded that these zones represent a potent force beyond our reach, demonstrating once again the profound limitations of human exploration. Moving forward, let us now explore another perilous phenomenon that showcases the universe's extremes: magnetars. Stars with magnetic fields so intense that they challenge all understanding of physics. Now turning to the next challenge, we encounter one of the most extraordinary and perilous phenomena in the cosmos: magnetars. These are highly magnetized neutron stars, remnants of supernova that pack an incredible amount of mass into a sphere barely 20 kilometers wide. What sets magnetars apart is their staggering magnetic fields, which are trillions of times stronger than the magnetic field of Earth. To put this into perspective, the magnetic power of a magnetar is so immense that it can distort the atomic structure of matter at a distance of thousands of kilometers. If a spacecraft were to approach even remotely close to one of these objects, the intense magnetic field would wreak havoc on its electronics, tear apart its structural integrity, and render any instruments completely useless long before it could get anywhere near the star itself. Moreover, the surface of a magnetar is an unthinkably hostile environment, with temperatures soaring into the millions of degrees and bursts of radiation, known as giant flares, occasionally releasing in a fraction of a second more energy than the Sun emits in hundreds of thousands of years. These flares are so powerful that their impact can be detected across vast stretches of the universe, and in rare cases, they can even disrupt satellites and communication systems here on Earth despite being located thousands of light years away. The unparalleled intensity of magnetars not only makes them completely inaccessible for direct exploration, but also places them among the most extreme objects in existence, defying much of what we know about physics. Studying them from afar using advanced telescopes has revealed tantalizing details. Yet many questions remain unanswered, such as how they form and what drives their incredible magnetism. As we ponder the mysteries of these cosmic powerhouses, we are reminded of the universe's capacity to push the boundaries of what we once thought possible. Moving forward, let us now journey to another enigmatic region of the universe, the Eridanus supervoid, a colossal expanse of emptiness that challenges our understanding of cosmic structure. Now turning to the Eridanus supervoid, we encounter a baffling region in the cosmos that seems to defy everything we understand about the large-scale structure of the universe. Located in the constellation of Eridanus, this supervoid is one of the largest known gaps of its kind, stretching over 1 billion light-years across. What makes it so extraordinary is not just its size, but its profound emptiness. Unlike the dense, vibrant areas of the universe overflowing with galaxies, stars, and cosmic activity, the Eridanus supervoid is hauntingly sparse, with far fewer galaxies than expected within its immense boundaries. This vast expanse of near-nothingness has left astronomers puzzled since its discovery. It challenges models of cosmic evolution, raising questions about how such a colossal void could have come to exist. Some theories suggest that it could be the result of random fluctuations during the early stages of the universe's formation, while others propose that it might be tied to phenomena we do not yet fully understand. Adding to the intrigue, this region has also been linked to the mysterious cold spot observed in the cosmic microwave background, a relic of the universe's earliest moments. While it is still debated whether the two are connected, the idea that this enormous void could have had an impact on the very fabric of the universe is both fascinating and humbling. Unfortunately, the sheer scale and emptiness of the Eridanus supervoid make it impossible to explore directly. With no substantial matter to emit light or radiation, it is shrouded in darkness, leaving us reliant on indirect observations and simulations to piece together its story. This enigmatic void serves as a stark reminder of the universe's complexity, showing us that even in the apparent nothingness, there are riddles waiting to be solved. As we leave the ineffable silence of the Eridanus supervoid behind, we turn our gaze to the final chapter of this journey, a concept so speculative and boundless that it lies at the very edge of science and imagination, the multiverse. With the next phase of the journey in sight, we arrive at a concept that pushes the boundaries of both science and imagination, the multiverse. This theoretical idea suggests that our universe, vast and incomprehensible as it already seems, might be just one of countless others. These parallel universes, if they exist, could differ from ours in unimaginable ways. Some may follow the same physical laws, while others could operate under entirely different principles. The concept of the multiverse arises from several fields of science, including quantum mechanics, string theory, and cosmology. In the realm of quantum mechanics, for instance, the multiverse is linked to the idea that every decision or event creates a branching reality, leading to an infinite number of alternate outcomes. Meanwhile, string theory proposes that multiple universes could exist as part of a larger framework known as the cosmic landscape. Cosmologists have also speculated that the rapid inflation of space shortly after the Big Bang might have generated countless isolated pockets of spacetime, each forming its own universe. Despite its allure, the multiverse remains an idea that is inherently beyond our reach. These other universes, if real, are separated from ours by barriers we cannot cross, such as different dimensions or vast expanses of space and time that make direct interaction impossible. They leave no observable traces within our own universe, making them a challenge to prove or disprove with current scientific tools. Yet, the implications of the multiverse are profound. If it exists, it could revolutionize our understanding of our place in the cosmos. It raises deep philosophical questions, too. What would it mean if our universe is just one of many? Could other versions of ourselves exist in these parallel realities? Do these countless universes reduce the significance of our own existence? or does their sheer possibility enhance the sense of wonder we feel about the cosmos? While the multiverse remains a speculative frontier, it serves as a powerful reminder of the vastness of human curiosity. It dares us to question the limits of our universe and challenges us to think beyond the confines of what we can see, measure, or even imagine. And with that, we conclude our journey through these enigmatic regions of the universe, venturing from the tangible and near to the theoretical and boundless. Together, they reveal a cosmos filled with awe and mystery, urging us to keep exploring, questioning, and reaching for the stars. As we bring our journey to a close, let us take a moment to reflect on the enigmatic wonders we have explored. From the vast cosmic voids to the fiery cores of galaxies, from mysterious black holes to the tantalizing concept of the multiverse, each of these regions reminds us of the profound limits of our reach. Yet, paradoxically, it is these very limits that ignite the flames of human curiosity. The inability to venture into these distant realms or unlock their secrets with current technology does not diminish their significance. Instead, it drives us to innovate, to discover, and to dream beyond what seems possible. These regions of the universe are more than just unreachable destinations. They are testaments to the infinite scope of existence and the endless questions waiting to be answered. What other marvels might await us beyond the edges of our knowledge? One day, perhaps, future generations will achieve technological feats we cannot yet imagine, bringing us closer to unraveling these cosmic enigmas. But for now, let us embrace the mystery, for it is the unknown that pushes us to explore new frontiers. What do you think lies beyond the boundaries of what we can observe? Share your thoughts in the comments below, and be sure to like this video and subscribe to our channel to continue this infinite journey through the cosmos. Thank you for watching, and until next time, keep reaching for the stars.